Hello, Gabriel. Good to see you again. I hope you are doing well. And good, you can hear me. That's good. So this is our last class about combinatorics. So during this, the last 3 weeks, right, we talk about number one, what is it? Arrangement of objects, and after that pigeonhole principle, then permutation and combination. And now we have a test. Okay, in test, we are going to practice a few questions related to the problems that we have already studied, and that's it. So I think there are, how many questions? There are I think about 15 questions, I guess. So step by step, we try to solve all questions in detail. And of course, in math, the most important thing is gaining intuition. It's not about only learning the method. Okay, well, look at the things when you're solving the problems. What do you feel? Does it give you some kind of feeling that what's going on behind the scene? That's the most important thing, I guess. And that's what you are trying to achieve here. Otherwise, okay, just plus and minus, add and carry out a few operations to get something. That's it. No, it's not like something like this. What is the logic behind this? How things are connected to each other? Because since we are living in this world, right, that you see that everything is related to each other, right? The motion of the sun and the moon and the people's lives to each other and the countries and blah, blah. A lot of things, actually, almost everything is somehow they are related to each other. So let's start with this question then. John has 43 Chinese books, 81 English books, and 6 Japanese books. How many ways to take one book from them? And that is the first part, is about addition, right? If you remember, so solution. So I can just write here, John has some books, Chinese books. Let me just write the books all together with B. I can just put here his Chinese book number 1, Chinese book number 2, and Chinese book of 43. And after that, he has, what is it? English books, 81 English books. So let me just label this by E1, the first English book, the second English book, and he has 81 English books. And 6 Japanese books, that is Japanese 1 and Japanese 2, ... and Japanese 6, right? And in his collection, how many books are there? Here we have 43 Chinese books and 81 English books and 6 Japanese books. Altogether, that's 124 and 130 books. The question is that how many ways to take one book from them, right? If you just pick only one, either you can take one of these Chinese books or one of these English books or one of these Chinese books, right? And just picking only one. So how many different ways then? That is just we have 130 different ways, because you need to pick one of these books since we have 130 books. Question 2, it says there are 9 shirts, 7 pairs of trousers, and 4 ties. How many ways to select 1 shirt, 1 pair of trousers, and 1 tie are there? So how many, that means that how many ways are there to select 1 shirt, 1 pair of trousers, and 1 tie at a time, right? So let me just write here shirts. Let me just write here shirts, right? Here we have how many shirts? 9 shirts. Let's say this T1 and T2. Let's say this T9. And 7 pairs of trousers. Okay, I can just write here also trousers, 7 pairs of trousers. Actually, the shirts, I should write S for this. Just write here S1, S2, and S9. Trousers, how many? It is 7. It is T1, T2, and T7. Here we have 7 different trousers. And ties, for ties, let me just write here, let's say this Q. Okay, that is Q1, tie Q2, and Q3, Q4. I mean, we should just imagine something like this. Here we have three different sets, right? The first set actually it is a collection of shirts. We have 9 different shirts. And the second one is 7 pairs of different trousers and 4 different ties. Okay. And usually when we go to work, right, we just pick one shirt and one pair of trousers and ties. After that, we just go to work, right? So that means that in how many different combinations we can make using this, so that actually we don't have any two of the combination. I mean, the same, we don't have any same combinations, right? How many different? At least there must be one small difference between that. Maybe your tie is different, or trousers is different, or what is it? Shirts is different. So at the time, actually, for this, right? For selecting shirts, we have 9 different ways, because I can pick one of these 9 shirts, right? And how about trousers? Trousers, I have 7 different ways. And how about tie? We have 4 different ways. So now here we have this many different combinations we can make using this set of, or what is that, outfits. So that is 9 times 7 times 4. That's equal to, what is it? That is not 252 different ways. So how many different ways? We have 252. That means that in your wardrobe, if we have 9 shirts and 7 t-shirts, I mean, pairs of trousers and 4 ties, right? You can just go to your school or go to work, whatever it is, go out in 252 different ways, okay? We can actually have different appearance. That's what we mean. It's a lot, right? Anyway, that's another example. Let's move on. Another question. There are 5 green clothes, 9 white clothes, 4 red clothes, and 7 blue clothes. Find the minimum number of clothes to be taken randomly, such that it is sure that means to ensure that at least 4 clothes have the same color. Okay, this is a little bit, I would say, tricky question, because a lot of students at once, they don't understand what we mean by this. And it is related to, what is some pigeonhole principle, right? So actually, I know one easy way to understand this question is, here we have green, okay, and here we have white, and here we have red, and here we have blue. How many green do we have? Here we have 5. And white, we have 9. And the red, we have 4. And blue, we have 7, right? So now, students think that, okay, if I just pick 4 green clothes, okay, then that's done. Just one is enough. That is the best situation here, right? So here, the keyword here is that we have to pay attention here is, what is it? It is to ensure that. So that means that to ensure, right? To ensure means that to be 100% guaranteed. So here we have to ensure. Okay, so we want to be 100%. We want to be 100% sure that actually we have 4 clothes of the same color. That's the point here. So then what is the worst scenario here? The worst scenario here is you just pick, every time you just pick the clothes, they are, it is different color. Like for example, you just pick green 1, white 1, and red 1, and here we have 1, right? And after that, green again 2, second one again. Every time we're just picking from the drawers, different color. And here also, here we have different color, right? So now when I just pick this many different colors, right? So as see here, we have 3 of each color, right? Now, if I just pick one more, okay, one more, whatever it is green or white or red or blue, it doesn't matter. Let's say I just pick one more, it is white, for example. And say I have already, what is it, 4 clothes of the same color. And if you pick another one, for it's red, again, it will be 4 clothes of red color, right? So that means that here we need to pick how many? 13, right? Because here we have 4. So each one actually contains 3, and that's like, what is it? Here we have 4, okay. And maximum I can just write here, for example, from each color, right? 1, 2, red 4, and 1, 2. Sorry, we have 4, right? 4 colors. Okay, here we have, I can put here red, green, white, white, red, red, and blue, blue, right? So now if you just pick one more clothes here, I need to put this either into this shelf or this one or so, wherever you put this, right? Actually, you will get 4 clothes of the same color. So our pigeonholes here is, what is it? We have 4 pigeonholes. Okay. So 4 pigeonholes to have the same one. Actually, the answer is, what is it? 4 times 3, it is plus 1. That's equal to 13. So that means that if you just pick 14 clothes, I can guarantee that 4 of them will have the same color. Okay. Let's continue. Another question, question 4. Some students buy Chinese books, mathematics books, and English books. Any one of them buys 1, 2, or 3 books. Each student buys at most 1 book on each type. Find the minimum number of students such that it is sure that at least 3 students buy the same combination of books. So, solution. And also last time we did a similar question. Here it says that any one of them buys 1, 2, or 3 books. Each student buys at most, here it says at most 1 book, right? Maximum on each type. They cannot buy 2 Chinese books or 2 English books, but at most 1. And find the minimum number of students. We need to find the minimum number of students such that it's sure that, again, it is sure that at least 3 students buy the same combination of books, right? So actually every student should buy at most 1 book each type, right? Any of them can buy 1, 2, or 3 books. Now let me just leave like this. So when they just buy 1 book, what are the possibilities? They can buy maybe 1 Chinese book, or 1 math book, or 1 English book. And how about if a student buy 2 books, for example, 2 book collection, okay? So maybe he can buy Chinese math book, or Chinese English book, or math English book. Because in the question it says that at most 1 book, right? He cannot buy 2 books of the same language or the same subject, same. And also 3 books, let me just write here, 3 book collection. What are the possibilities of 3 book collection? They can buy 1 from each, right? That is Chinese, math. Actually, I need to write it like this: Chinese, math, and English, right? So we have how many different combinations we can make here? 1, 2, 3, 4, 5, 6, 7. So that means our pigeonhole here is actually this 7. We just write here like this. So here we have maybe 1. Okay, here we have 6. We just draw like this. And I have 1 more small hole here. So that is 7, right? So I can just write this C, M, E, C, M, and C, E, and M, E. Now C, M, E. We don't have any other possible combination here, right? So that means that, for example, if we have 7 students, they can, actually everybody may have different collections, right? So here, since here we have, let's say, pigeonhole is 7, the question is minimum how many students? At least students buy the same. So that means that here, it's right here, number of students, right? And using that floor ceiling function, that should be equal to 3, right? So if n is equal to 14, we know that 14 over 7 is 2. The ceiling of 2 is 3. I mean 2. So it's not the answer, right? It should be 2 point something, which means that here the minimum value of n here is, it is 15. Because 15 over 7, it is 2 point something. What is the smallest integer that is greater than or equal to 2 point something? That is 15. So if we have 15 students, I can guarantee that 3 students will have the same collection of books or the same combination of books. Okay. Question 5. Evaluate, just to warm up again, to evaluate this, the formula, if you remember, let me just write one more time. Permutation of n objects taken r at a time, right? That's equal to n factorial over n minus r factorial. So from here, then P 8, 5 here, the permutation of let's say choosing or arranging of, for example, what is it? 8 objects, right, taken 5 at a time. I mean, we are just arranging 5 objects taken from this 8. Anyway, that's equal to 8 factorial over 8 minus 5 factorial, which is equal to 8 factorial over 3 factorial, right? Which is equal to 8 factorial. We can write it as 3 factorial times 4 times 5. That is 3 factorial times 4 times 5 times 6 times 7 over, here we have 3 factorial, which is equal to 4 times 5, 20, 20 times 6, 120, 120 times 7, it is 840. And how about for combination? Combination, right here we have 13 and 8, that is 13 factorial over 8 factorial, and the difference, 13 minus 8. So that is 13 minus 8 factorial, which is equal to 13 factorial. I can write it as 8 factorial times 9 times 10 times 11 times 12 times 13 over, here we have 8 factorial times 13 minus 8 is 5. 5 factorial, I can write it as 1. Don't have to write 1, 2, 3, 4, 5. So these guys are gone. And with 10, 2, and 5, also it is gone, right? With 3 times 4, it is 12. Also this 12 is gone. So that's equal to 9 times 11, 99. 99 times 13, what is it? It is 100, 130. 99 times 13, that's equal to 1287. Gabriel, is everything okay? Good. Okay, another question. How many ways to put 4 distinct tables into 7 rooms? No room has more than one table, right? So again, it's the same question like where we have 7 rooms, right, at a time, and how many different ways we can choose 4. Because it says how many ways to put 4 distinct tables into 7 rooms, right? That means that here we have 7 places, right, or 7 rooms. So at a time, we need to choose 4. That's just combination, right? Combination. So here we have, what is it? It's just C. Here we have 7 and 4 because we have to select 4 rooms out of this 7, right? So that is equal to 7 factorial over 7. Here we have 4 factorial. 7 minus 4, it is 3 factorial, which is equal to 7 factorial is 4 factorial times 5 times 6 times 7 over 4 factorial. 3 factorial is, we know, this 6. That's equal to, these guys are gone. And also this one is gone. So that's equal to 35 different ways we can choose. Okay. Another question, and after that we'll give 1 minute break. How many ways to put 6 identical tables into 10 rooms? No room has more than 1. So how many ways to put 6 identical tables? The previous one, it is distinct tables, 7 rooms. With here, identical tables, it doesn't matter. So okay, again, it's a similar question. Here we have 10 rooms, right? We need to put 6 identical tables in 10 rooms. No room has more than 1 room. So that means that at a time, and how many different ways we can choose 6 rooms, right? So this is just the combination again. Here we have, because we are selecting, we need to select 6 rooms out of this 10 at a time. So that is 10 factorial over 6 factorial. 10 minus 6, that is 4 factorial. So that's equal to 7 times 8 times 9 times 10. The 6 factor is gone. What is 4 factorial? It is 2 times 3 times 4. Now from here, 8 and 2, 4 is gone. 9 with 3, it is gone. Here we have 3. 7 times 3 is 21. 21 times 10 is 210. Okay. Now give me 1 minute. Let me bring my tea. Okay, then we'll continue. Okay, I'm back. Okay, thank you. All right, now let's solve a question from part B. How many 3-digit even numbers with distinct digits are there? So how many 3-digit even numbers with distinct digits are there? So it says even numbers, right? So solution. We know that what numbers are even numbers if the last digit is 0, 2, 4, 6, 8, right? So if the last digit is 0 or 2 or 4 or 6 and 8, those numbers will be, what is it? Distinct number. So this is the first and the second and third, right? So we are talking about 3-digit number. So for the last digit, right, it must be one of these numbers. So how many different numbers I can put here? We have 5 different numbers or possibilities, let's say. So, and how about the second one? Since I have already used one of these, right? Actually, I can choose for the second place one of the digits, right? Because from 0 to 10, we have 0 to 9, we have 9 digits, but I cannot use this. Okay. So, all right. So for the first place here, I cannot use any of these even numbers. So that means that we have 10 digits, only 9 left. So I have here 9 possible answers, right? For example, if I use 5 here, I can use all the digits, but not 5, right? How about for the first place? I cannot use 0, otherwise it will not be 2-digit number. I cannot use a number that's used here. I cannot use a number that's used here, right? So 3 is out. So here we have, actually, I cannot use 0. I cannot use, this number is used here and here. So here we have 7 possibilities here. All right. So then here we have 9 times 7 times 9 times 5, which is equal to, what is it? 7 times 9 times 5, that's equal to 350. Distinct. Okay, let's continue then. Question 2, how many integers with exactly 2 8s from 1 to 10,000? How many integers with exactly 2 8s from 1 to 1,000? All right. So this question is, we don't have a short way. I would, at least what I know, okay, but step by step, we will try to find the numbers. So first, let me just consider number 1 is, here we have number 1, number 2, number 3, and number 4. Okay, now I can write later. How about the 1-digit number? Okay, so 1-digit number, it does not contain any 2's, right? The number of such numbers is, it is 0. And how about if you're talking about 2-digit number, we have only one number that contains 2 8s, right? What number it is? It is 88. Let me just write here, that's only 88. So we have only one such number. And how about if you're talking about 3-digit number? Okay, so when we just talk about 3-digit number, and what are the possibilities that we can write 2 8s? Maybe I can just write 8, right? And any number here, or 8, any number here, 8, or any number here, not 0, and here we have 8, 8, right? So if I just write here 8, 8, for example, right? 8, 8, how many numbers I can write here? I can write 0 or 1 or 2 or up to 9, but not 8, right? Because it should have exactly 2 8s. So that's why here we have 9 different ways. And how about here? Here we have, again, I can just write any digit, right? But not 8, because it already have written 2 8s here. So again, here we have 9. And how about in this case, the first digit, it cannot be equal to 0. It cannot be equal to 8. So how many digits left? We have only 8. So together then, how many such numbers do we have with 2 8s? We have only 18, 26. Okay. So simply in other way, how do you find this? Actually, this, I can write this here or here or here, right? We have a combination. Actually, this 26 is combination. There's 3 places, right? I can choose 2. I mean, writing these 2 8s in how many different ways? You see here, I can write 3. That's a combination, right? Selecting 4 places for 8 times, and after that, the permutation, and I can choose one number out of 9, right? And also the just one digit 0, it cannot be here, that's equal to -1. So if we calculate this 3, here we have 3 factorial over 2 factorial, that's equal to 3, and this one is 9 factorial over 8 factorial, that's equal to 9. So -1, that's equal to 26 using combination. If you understand this one, now also we can do the third one in a much easier way. And how about the fourth case? Fourth case is, how about if you're talking about 4-digit number, right? The 5-digit number, 10,000, it doesn't have any 8, 8, all numbers less than, 4-digit numbers, right? That's less than 10,000. Anyway, so how many ways can I write 8 here again now? So I can write 8, 8. Let me just show you some examples. 8, 8, any 2 digits here, right? Or 8, any digit here, 8, and the blah, blah. How many? So this one is just combination. We have 4 places to put 2 8s, right? So that's equal to, what is it, 4, actually, if you just calculate this one, actually, that's equal to 4 factorial over 2 factorial, 2 factorial, that's equal to 4 times 3 is 12 over 2. That's equal to, it is 3, 4. Okay, 2 factorial is gone. 4 times 3, 12, 12 over 2, it is 6, right? It is 6. So let me just write, it is 6. I can just write like this, 8, 8, here we have like this, or 8, dot, dot, here we have 8, 3 ways. And the second one is 8, so here we have 8, 8, dot, dot, 8, dot, 8, right? The last one is dot, dot, 8, 8. So we have 6 different ways, okay? Anyway, so after that, writing, what is it? Again, so now we have to choose, for example, 2 numbers, right, out of 9 numbers. So that's just permutation then. Permutation, we have 9. It's just because I cannot use 8. So out of these numbers, we have to choose 2 of them, right? For each, for example, for 8, 8, combination here, for another one, combination. And from here, minus, also the first digit cannot be equal to 0. I have to subtract this, right? So that is combination for 3 places, right? I have only 2, that's we have only 3, because if the first one is empty, right? How many different ways I can write 8, 8? That's, for example, empty. I can write 8, 8 empty here, or empty 8, empty 8, right? Or empty, empty 8, 8. We have 3 different ways. This is how we calculate the number of possibilities that the first digit is 0 times now the permutation. So again, we are just choosing now how many numbers we're choosing, because not 0, right? It is 8, right? Just 1, because we are given the remaining numbers 1 to 7 and 9, right? Not 0, not 8. So we're just subtracting this. Anyway, from here, what is this? 3, 2, that is 4 factorial over 2 factorial times 2 factorial times permutation of 9 out of 2, that's 2 out of 9, that's 9 factorial, 9 minus 2, that is 7 factorial. Minus, here we have 3 factorial, 3, 2 factorial, and 1 factorial. Times permutation, here we have 8 factorial over 7 factorial. So the first one is 2, 2, it is 4, and 4 is gone. 2 times 3, here we have 6. Times, this one, the 7 factorial is gone. Here we have 8 times 9. Minus 3 factorial, right, is equal to 3. And 8 factorial over 7 factorial, that's equal to 8. So which is equal to 6 times 8, 48, 9 times 48, and minus 24, that's equal to 6 times 8 times 9, that's equal to 432. 432 minus 24, which is equal to 408. So that means that here we have 408 4-digit numbers which contain 2 8s. So now we can just write our final answer. The final answer is dot, dot, dot. When it is 1-digit number, it is 0. When it is 2-digit number, we have only 1. When it is 3-digit number, we have 206. When it is 4-digit number, we have 408 such numbers, which is equal to 409, 415, 435 4-digit, integers from 1 to 10,000, which has exactly 2 8s, and it is, what is it? And it is notation. All right, let's continue. Next question. Here, how many ways to put 4 identical coins into the square of a 2x2 chessboard, such that there are 2 coins on each row and each column? Okay, so part A, just use purple here. how many ways to put 4 identical coins into the square of a 2 by 2 chessboard, such that there are 2 coins on each row and each column? That's only one way, right? Because if you're talking about a 2 by 2 chessboard, it is like this. And I assume that we cannot put more than 1 coin into each square. So I can put just 1 coin here because we have only 4, and we can put here, and we can put here, and we can put here, right? So how many ways? There's only one way, right? So in part B, it says how many ways to put 6 identical coins into the squares of a 3 by 3 chessboard, such that there are 2 coins on each row and each column. So now here we are given a 3 by 3 column, the square chessboard. Okay. So now we need to put 6 identical coins, right, into the squares of a 3 by 3 chessboard, such that there are 2 coins on each row. But the first one, for example, how many different ways I can actually put this 2 coins, because it must contain only 2. We have 3 actually places, right? And I need to choose only 2 of them, which is equal to, actually, if you calculate, this is 3 factorial over 2 factorial times 1 factorial. We have 3 different ways, right? Let me just show here. It's like, maybe I can write A, let's say it's our coin, and this one is empty, and this is our coin, or A, this is empty, right? Or empty place. Here we have coin and coin. We don't have any other possibilities, right? So we have 3 different ways. Okay. So now, how about the second part? Okay, in the second part, now, actually 2 coins, they cannot be, for example, let's say if I just put A and A here, maybe one of them should contain A, right? For sure, right? Because we have only 3, but I cannot put here 2, because if it is 2, we have 2, there will be a problem here. Maybe I need to put here. So that means that actually for each, we have only 2, for each, for example, for this one, we have 1 way. For another one, we have 1 way. For the third one, we have only 1 way. So that's why here we have only 3 different ways. So for this, we have 3. For this, we have 3. Then here we have for each, what is it? No, we have 2 different ways, right? We have 2 different ways. So for the first one, then we have the first column, we have 3 different ways. For the second one, we have 2 different ways. And for the last one, we don't have any other way, only one position, that's equal to 6. Because here I can just write it like this, or also I can just write it like this, right? For each. So for this, we have 2 possibilities. Now, after writing this for the third one, for example, I have only 1. So I need to write here only here and only here. We don't have any other choices here. So for the first column, we have 3 different ways. For the second column, we have 2 different ways. And for the last one, we have only 1 different way. So in 6 different ways, we can just make this. I can just show you some of them. Again, for example, let's say cross means of a coin. Cross means maybe it's coin, like this coin, cross, right? And here we have cross, maybe coin. And here we have coin again, and cross, and here we have coin. 1 possibilities. And this way you can just see that it's 6 different ways. Anyway, another way, I don't know, let's see, we'll see another question, and this is the only way I can do this. Question 4, in question 4, evaluate. Again, just this one is to consolidate your knowledge about calculating, what is this, combinations. So here, solution. So it's all different, right? 3 0, 3 1, 4 2, 5 3, 6 4 6 4, 7 5, 8 6. What can we do? Just we need to write 1 by 1 and calculate this. So that's equal to 3 0. What is it? It is 3 factorial over, here we have 0 factorial times 3 minus 0, that is 3 factorial. Second one is 3 factorial over 3 minus 1, 2 factorial, and here we have 1 factorial, or just 1 factorial, 3 minus 1 factorial. I can just write it like 1 factorial, 3 minus 1, it is 2 factorial. And the next one, 4, 2, that is 4 factorial over 2 factorial, 4 minus 2, it is 2 factorial. And here we have 5 factorial over 3 factorial, and 5 minus 3, it is 2 factorial. Next one is 6 factorial over 4 factorial, 6 minus 4, it is 2 factorial. And 7 factorial over 5 factorial, 7 minus 5, it is 2 factorial. We have 8 factorial over 6 factorial, 8 minus 6, it is 2 factorial. Equals the first one, 0 factorial, we know this defined as 1, 3 factorial over 3 factorial, that's equal to 1. Second one, 3 factorial, right, over 2 factorial. That is 3 times 6 over 2, so that's equal to 3. Next one is 4 factorial, that is 24 over 2 times 2, that is 4. Next one is 5 factorial. We can just write this 3 factorial, right? It's 4 times 5, 4 times 5 over 2, that is 10. And here we have 6 factorial, 4 factorial is gone, and 5 times 6, 30, 30 over 2, that is 15. And also, let me just write it, 24 over 4, that is just 6. 1 plus 3 plus 6 plus 10 plus 15. I think next one will be 25, right? It is, no. Next one will be 21. Anyway, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, 6, 7 factorial. 5 factorial is gone. 6 times 7, 42 over 2, that is 21. Next one is 6 factorial is gone. 7 times 8, 56 over 2, that is 28. Okay. So this one is 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 3, 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4 plus 5, and 6 is just, what is it? The sum of the first 1, 2, 3, 4, 5, 6, 7 natural numbers. Anyway, 1 plus 3, 4, 4 plus 6, 10, 10 plus 10, 20, 20 plus 15, 35, 35 plus 21, 56, 56 plus 28, 70, 84. So that's equal to 84. So the whole thing here is equal to 84. Another question, evaluates. All right. So usually this combination, one of the application of the combination is in binomial expansion. Binomial expansion means, for example, if we have a plus b to the power of 1, right? It's just, let me just write here, to the power of 0. It is just equal to, we know that it's equal to just 1, right? And a plus 1 to the power of 1 is equal to just a plus 1, a plus b. And a plus b squared, that's equal to a squared plus 2ab plus b squared. Okay, and let me just write one more time, a plus b cubed, for example, that is a squared plus 3a squared b plus 3ab squared plus 1. Now continue. If you just notice here, that what's going on here. The first one starting with 1. The second one, coefficients of a and b is 1 and 1. Third one, it is 1, 2, 1. So that is 1, 2, 1. Third one is 1, 3, 3, 1. That is 1, 3, 3, 1. Next one will be 1, 4, 6, 4, 1. I'm just adding 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, and it's 1. Next one will be 1, 5, 10, 10, 5, it is 1. What are these numbers? These are just the coefficients of this binomial expansion. We are saying binomial because it has two terms. If the power is 0, the coefficient will be 1, just 1. If it is 1, the second one. If it is 2, third one. If it is 3, and this one is 4, and this one is 5, it continues. In general, actually, if you just notice here, for example, this 5, right? Number 5 is, if you just calculate for 5, for example, n is equal to 5, what happens here? Here we have, if you just calculate this, C5, 5. What is it? It's just equal to C5, 5 is equal to 1, because 5 factorial over 5 factorial times 0 factorial, that's equal to 1. And how about C5, 4? That's equal to 5. And C5, 3, if you calculate this, that's equal to 10, because 5 factorial over 3 factorial, 2 factorial, and 3 factorial is gone, 4 times 5 over 2, that's equal to 10. You see here, it's just giving us the coefficients of this. And that's why in binomial expansion, one application of combination is this. Let me just write here, because now we're going to prove this. Why is it so? So if we have a plus b to the power of n, okay, so that is equal to the coefficients. Here we have c and n, and here we have a to the power of n, plus c, here we have n minus 1, and here we have n, a to the power of n minus 1, here we have b. And just continue. If you just write only the coefficients, coefficients will be like this: a, c, and n plus, not c, let me just not write n m. Here we have c, n, n minus 1, c, n, n minus 2, dot, dot, c, n 1, and c, and 0. So these are just the coefficients of any binomial expansion of a plus b to the power of n. And here we have the powers of a and b, okay? The power of a is decreasing and power of b is increasing. Here we don't see power of b because it's b to the power of 0. That's why. So using this one, actually, how do we calculate this then? C to the power of 10, 0, c to the power. If you just consider this polynomial function, p of x, that's equal to x plus 1 to the power of 10. Okay. So what happens if, for example, x is equal to 1? Okay, if you just open this, expand this, here we have c, here we have 10, it is 10, or maybe I can start with 0, it doesn't matter actually. It is 10, 0, here we have x to the power of 10, plus c, 10, and 1 here, x to the power of 9, because the second one is 1, 1 to the power of anything is just 1. And plus c, 10, here we have 2, x8. And continue, here we have c, 10, here we have 1x, and c, 10, 0, and here we have x to the power of 0, that's just equal to 1. So now if you just evaluate the value of this polynomial at 1, here we have p of 1. On the right-hand side, I have 1 plus 1 to the power of 10. On the right-hand side, x is equal to 1, so here we have c, 0, 10, plus c, here we have 10, 1, plus c, 10, 2, dot, dot, here we have c, here we have 10, 0. Sorry, 0, 1, the last one will be 10. So that's just the sum of the coefficients of this. So that on the left-hand side, what we have here, 1 plus 1 is equal to 2. So that's just equal to 2 to the power of 10. And which is equal to 2 to the power of 10 is 7, 1, 28, 8, 9, 512, that's equal to 1024. So that is one application of this combination. So that's just equal to 2 to the power of 10. That's equal to 1024. Okay. Let's continue. Part C. So in part C, we have 2 questions, I guess. Yes, in addition, question 2 questions, and we will finish today's class. Prove that if 11 numbers are chosen from 1 to 320, then there are 2 numbers such that one of them is a multiple of another. Okay, so here we are going to use pigeonhole principle to prove this. The first, we have to identify our pigeonholes, and after that we have the number of pigeons, then can get the answer quickly. So we have to choose numbers from this, right? It is solution. I'm just going to make a group of these numbers, all right, in such a way that the first one is, here we have A, okay, we are actually, I'm just creating my pigeonholes. I just put in the first hole the numbers which are the multiples of 1 and 2, 4, 8, and 16. Actually, 1 I can put anywhere here, but I want to put it here. 1 times 2, 2 times 2, 4 times 2, 8. That means that if you just pick any two numbers here, they are actually, one of them is a multiple of another. For example, if you just pick 1 and 2, 2 is a multiple of 1. If you pick, for example, 2 and 16, 16 is a multiple of 2. For example, if you get 4 and 16, so that 16 is a multiple of 4. So in this way, I'm just grouping these numbers. In the second group, I'm going to put these numbers, 3, 6, 12. 3 times 2, 6, 6 times 2, 12. As you see here, if you just pick any two numbers from here, one is a multiple of another one. In this way, 5, 10, 20, and 7, 14, and 9, 18. 10 we have already put here, and here we have 11 because just a prime number, and 13, and 15, 17, 19. And I have put all of these numbers into these holes, right? Altogether, how many numbers I have written here? 20 numbers. So how many such pigeonholes here? Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means our pigeonholes here, let's say, is equal to 10. Okay, so I can just put them here. For example, into the first hole, I can just put, for example, this A. Into the second one, it is B and C and D and E and F and G and H and I, J. I can just write this, okay? So if you just put this one here, right? I just take one number from A, just one. How can I write this? One element from A, let me just write it as A. One number from B here, one element from C, one from D, one from E, one from F, one from G, one from H, one from I, one from J. Okay, just one number, I put them here. So that is the number of holes we have, right? Now the 20 means we have 20 pigeons here. So now if I just pick any number from these numbers, right? If we just, I need to put into one of these holes, right? Into A or B or C or D, wherever you put here, if you just pick any number here, right? Actually here we have, if you just combine these numbers, we will see that actually we will have at least one number that will be a multiple of another number. Why? Because you need to take these numbers. For example, if you take one number from A, here we have A, right? We know the two numbers here. If you just pick two elements from A here, one of them will be a multiple of another. If you take B, here we have one element from B. If you take from C, we have one element from C. If you take from D, we have one element from D. Right? In this way, actually, of course, F, G, H, I, they have only one already put, we cannot take from here. So in this way, actually, since our pigeons, actually this pigeonhole is 10, right? So if you just pick 11 numbers, I have 10 numbers here. If you just put one more number, I can guarantee that we have two numbers where one is a multiple of another number. So I can just write here that pigeons is, it is M. So that is N. What is our M here? We are looking for that. N is equal to 10, right? So this should be two numbers. It is 2. So what is the smallest number? Let's just find this. M is equal to 11. So if you just pick 11 numbers, right? We are sure that one number will be a multiple of another number. Another question, question 2. The teacher is taking photo for Michael, Johnny, and other 6 classmates. Find the number of ways if 8 students stand in rows, in 2 rows, 3 in the front and 5 behind. Okay, so solution. And the front, right? The front, let me just write here, draw here front, it is 1, 2, and 3, right? At the back, 5. Here we have 1, 2, 3, 4, and 5. Okay, so in this way, this one is front, this one is, let's say, back. We are taking the picture, somebody taking a picture from here. Okay, so the question is, what is it? The teacher is taking a photo for Michael, right? And Johnny and other 6 classmates. Find the number of ways if 8 students stand in 2 rows, 3 in the front, 5 stand in the behind. So in the first one, suppose that the first case here is, just write in different color here. The first case here, suppose Michael and Johnny, they stand in the first row. Okay, so this Michael and Johnny, okay, they are standing in the front. Okay, front. In front, we have 3 places, right? In how many ways we can arrange this to? It's just the permutation, right? So that is when actually sitting in the front, we have first, I have to choose, what is it? Out of 3, we have 2 different places. And also we have permutation now, because here we have remaining people, 6 people. I can choose 1 person from the 6 people in how many different ways? That is 6 out of 1 out of the 6, right? And times. And how about the second row? Also second row, we have 5 students, right? We have to arrange these 5 students. So for 5 places. That's again just permutation, 5 out of 5. That's it. Because the first one is how we can select 2 people, right? From this, that means we are locating these 2 people. And after that, for each, we have 6 different possibilities. I can choose 1 student from the remaining students, right? And the remaining ones, I can actually arrange them in the second. So that's equal to, what is it? 6, C3, 2, that is 3 factorial over 2 factorial times 1 factorial. And 6, 1, that is 6 factorial over 5 factorial. And 5, 5, 5 factorial over 0 factorial, which is equal to, here we have 3, second one is 6, third one is 5 factorial. 5 factorial is, what is it? 4 is 24, 5 is 120, which is equal to 6 times 12, 720, 720 times 3, that is 2,160. So if these 2 guys are standing in the front row, we can arrange them in 2,160 different ways. Now the second case is, how about Michael and Johnny? They are standing at the back. If they're standing at the back, let me just write here, if they are standing at the back, Michael and Johnny, okay, they are standing at the back. So then this will be equal to, in the first front row, right, we have, I need to choose, okay, first, let me just start from the back then. Okay, from the back, that is, what is it? For combination, right? And we have 5 places. So we need to choose 2 for Michael. Okay. All right. Times the remaining students, we have 3, right? We need to choose 3 times 3. Because for the first row, right, I can choose 3 students out of 3. The remaining 3 students, there's 3 places, which means that we have 6 different ways. And for the front, back row, right, I can choose 2, right, for 5 different places. I have this permutation, or actually, it is taking a photo from Mark and Johnny. Other is find a number of ways if 8 students stand 2 rows, 3 in the front, 5 and behind. Michael and Johnny stand in the same row. Okay. All right. So Michael and Johnny say in the same row. The order is not important. So that's equal to 5, 2. That is 5 factorial over 2 factorial times 3 factorial. And here we have 3, 3. We know this just equal to 3 factorial. And also this one is 3 factorial. And this one is 3 factorial is gone. 5 times 4, 4 times 5, 10. 20, 20 over 2, that's 10. And 3 factorial, it is 6. And here we have 6. That's equal to 306. So in total, how many? That is 216 plus 360. That's equal to 2, 5, 20 different ways. Because in the question it's saying that Michael and John stay in the same row, actually the order is not important, right? If it is important at the time, we need to use with combination. If they say that Michael comes from before Johnny or on the right hand side or left hand side, doesn't matter. Here that's why. Anyway, so let me just skip one question and do one, and I'll finish the class. We are running out of time. So here, find the minimum number of positive integers to be written to ensure that there are 4 numbers A, B, C, and D, such that A minus B times C minus D is a multiple of 2009. And here the question here is the minimum number of positive integers to be written to ensure that there are 4 numbers is a multiple of this number. So solution. First, what is 2009? 2009, actually the factors of 2009. What are the factors of 2009? Let me just write them. It is 1 and 7 and 41, 49, 49 and 287, 287 and 2009. So these are the factors of 2009. So that means that 2009, I can write it as 1 times 2009 or 7 times 287 or 41 times 49. So the question is, we need to find the minimum number of positive integers, right? Minimum number to be written to ensure that there are 4 numbers A, B, C, D. Okay. So at this, how many number we should write? For example, okay, positive integers, of course, starting from 1. As you see here, if I just write like 1 or until 7 or until 41, so this one is, if I just pick this one, right, the difference is 1, the difference is 2009. We need to write a lot of numbers. Also here the same thing, but here actually this gives us some idea about writing this one. So now if I just write this set, okay, if I just write the numbers from 1 to 1, 2, 3, 4, and 41 and 42 dot dot, and here we have 49 and 50. Okay. So now if I just write 50 numbers here, right, and I'm sure that at least we have 4 numbers here. Okay, the year difference is 41 and the year difference is 49, so that it will be a multiple of 2009. So that means that 49, how can I have 49? Pick 1 and 50, that is 50 minus 1. Times, how about 41? Let's say it is 45 minus 4. So that's equal to 2009, the smallest one. Right? So at least if I just write 50 positive integers here, okay, I'm sure that we have 4 numbers here. So actually the product of the difference of 4 numbers will be 2009. Anyway, Gabriel, thank you very much. Okay, that's all for this combinations. Okay, combinatorics. Have a good day. All right, I wish you good luck in your studies. All right, bye-bye.